Hello, this is the last lecture of our course Introduction to Cryptology. We will be doing some problems on hash functions. I believe that you have enjoyed this course and you have also participated in the discussion forums. So, this lecture will be on some constructions or basically some toy constructions of hash functions, and we will be checking the kind of securities they do not have or sometimes they have. So, this is example 1. Example 1 says that let us suppose we have a bijection from 0 1 raised to the power m to 0 1 raised to the power m, which is pre-image resistant, and suppose we are going for some kind of iterative construction with this bijection. The iterative construction goes in this way. We are using f as a compression function and h is a function from 0 1 to the power twice m to 0 1 to the power m. So, please read 0 1 to the power m. Let me write over here. I have a function which I claim to be a bijection and pre-image resistant bijection from 0 1 to the power m to 0 1 to the power m. That means it takes m length strings to m length strings, and I am considering a function h from 0 1 to the power twice m to 0 1 to the power m. So, there is a misprint there that we will correct later. Now, how are we defining this function? Given an element x in zero 1 to the power twice m, we realize that we can split it into left half and right half. So, we will write x as x1 concat x2, where x1 belongs to 0 1, or let us write them together. X1 belongs, x1 and x2 belongs to 0 1 to the power m. Then h of x is defined as f of x1 bitwise XOR with x2. The question is whether, well, I have used in the slide x prime and x double prime, here I am using x1 x2, that is understandable. So, now the question is that whether this is second pre-image resistant or not. Now, let us look at this function. Suppose that we have got a pre-image image pair. So, suppose this is a particular x which is equal to, let us call it x, let us call it x0. So, suppose this x0 splits up into x01 and x02, or let me write like this here. Suppose x0 splits up as x0 prime and x0 double prime. So, I evaluate H on x 0 to obtain f x 0 prime XOR f x 0 double prime, and I claim that I have this value. Now, I have to find an x 1 which is not equal to x 0 and whose evaluation is this. This is not difficult, because suppose we take a string, let us say 1 and all zeros, altogether m bits belonging to zero 1 raised to the power m. Let us call this E 1. Now, let us construct a function like this, let us construct a point x 1 which is this x 0 XOR E 1 concat x 0 prime XOR E 1 and x 0 double prime XOR E 1. Now, one thing is sure, that x 0 prime plus E 1 is not equal to x 0 prime, because if it happened, then that would have meant E 1 equal to all 0 string, which is not so. It is also clear that x 0 double prime plus E 1 is not equal to x 0 double prime, the argument is again same. But if we, so therefore, we can say that x 0 is not equal to x 1, but if we evaluate the hash function at x 1, let us see what happens. H x 0 h x 1 equal to h x 0, we can directly write, we know that this is the left half and the right half. So, we can directly write f of x 0 prime plus E 1 plus x 0 double prime plus E 1, and therefore, f of x 0 prime plus x 0 double prime plus, that is XOR E 1 plus, that is XOR E 1. Now, we know that E 1 XOR E 1 bitwise is going to give me 0. Therefore, I arrive at f of x 0 prime plus x 0 double prime, which is equal to h of x 0. Thus, we see that we have obtained another point x 1 such that h of x 1 is equal to h of x 0, but x 1 is not equal to x 0. Thus, we have obtained a collision, a second preimage. So, this is this is why this construction leads to a hash function which is not second preimage resistant, although the compression function used is pre-image resistant. Here we have a we claim that we have a collision resistant hash function H1 which is a compression function in fact, and which is from 0 1 raised to the power 2m to 0 1 m. So, let me write it over here. H1 is a function from 0 1 raised to the power 2m to 0 1 raised to the power m, is a collision resistant hash function or compression function, and we have a scheme here which says that we are defining H2 from 0 1 raised to the power 4m to 0 1 raised to the power m as follows. I take an element of x belonging to 0 1 raised to the power 4m, I split it up into two parts, each part belonging to 0 1 to the power 2m. So, I am taking x inside 0 1 raised to the power 4m and split it up. So, I am splitting up x into x1 plus x1 concat x2, where x1 and x2 both are elements of 0 1 raised to the power 2m, and then I use the original concat function, sorry, original compression function. So, I get H2x is equal to H1 of H1x1 concat H1x2. So, this is my definition. Of course, H1 can accept a 2m bit string, and here also H1 can accept a 2m bit string, and H1 maps a 2m any 2m bit strings to an m bit string. So, I get an m bit string over here, I get an m bit string over here, joining them I have a 2m bit string. So, again H1 can accept this, I apply H1 on it, and I get the value of H2. So, that is my construction. Now, I am asked to prove that H2 is collision resistant. The question is how to prove this. What we do is that we in the beginning assume that it is not collision resistant. Suppose if possible H2 is not collision resistant, that means that I should be able to find a pair of elements of 0 1 to the power m which has the same image. Now, let us denote this pair by symbols. So, we have got a point, let us say x, and x splits up as x1. So, let us suppose this is one number, 1 point, and x prime which splits as x1 prime concat x2 prime. This is another string, and I am claiming that they are not same. X1 is not equal to x is not equal to x prime, that is my claim, or assume. Such, but I assume that this is a this gives rise to a collision. So, H2x is equal to H2 x prime, suppose that it happens. Now, let us try to see what are the logical consequences of this assumption. So, if this is true, that if I am able to find a collision in H2, then from this I will have H1 X1 concatenation H1 X2 is equal to H1 X1 prime concatenation H1 X2 prime. This is my definition. Now, one thing is clear to me, that by my initial assumption, initial claim, H1 is collision resistant. Therefore, if H2 is not collision resistant, we arrive at an equation like this, and since H1 is collision resistant, then I cannot get a collision, but these hash values are equal. That means hash values are equal means this forces me to say that H1 X1 concatenation H1 X2 is equal to H1 X1 concatenation H1 X1 prime concatenation H1 X2 prime. I am forced to say this. Suppose it is not so, that means I have obtained a collision of H1, which is not possible, and therefore, since these two strings are equal, then H1 X1 is equal to H1 X1 prime and H1 X2 is equal to H1 X2 prime. Well, again we know that H1 is collision resistant. So, when I have got an equation like this, it forces me to say that X1 is equal to X1 prime and X2 equal to X2 prime. But that means that this assumption contradicts this, but I am forced to say this because my basic claim is that H1 is collision resistant, and therefore, I cannot assume that H2 is not collision resistant. H2 is also collision resistant. So, what we see in this small problem is essentially what we studied in iterative constructions and Markle-Damgard construction. In the Markle-Damgard construction is more complicated, and it is quite elaborate, but it achieves ultimately the same thing. It says that if you assume that the compression function used in Markle-Damgard construction is collision resistant, then whatever you are going after iteration by using that rule is going to be collision resistant. So, this is, of course, this is not Markle-Damgard construction, but this is another construction, but which shows the same kind of property. Let us now move to the last problem of this session. So, this is a very easy problem. We will do this and close this series of lectures for the time being. It is a very easy problem. So, it just says that suppose that we have input data in the form capital X is equal to x0, x1, x2, x2 and to xn minus 1 such that xi are bytes. So, 8 bit these are 8 bit segments, and suppose my hash function is just summing up all these things, and let us assume that this sum is bitwise addition modulo 2, that is bitwise XOR, and so the question is this secure? The answer is it is not secure. So, we will do it just by taking n equal to 2. So, if we have n equal to 2, then the hash function is like this, h of x 0 let us say x 0 comma x 1 is sum x 0 x 1. So, let us look at this as a closing remark. So, we have got 2 bytes, one byte is 10 10 10. So, suppose I take x 0 is equal to 10 10 10 and x 1 is equal to 0 0 0 0 another 10 and x 1 is 0 0 0 0 1 1 1 1, add up 10 10 0 1 0 1. So, my hash value is this. Now, suppose I inverted the order, suppose I evaluated this over x 1 x 0, and of course, this sequence x 0 x 1 is not equal to x 1 x 0, and then I will also get the same result because this addition is commutative. This is 0 0 0 0 1 1 1 1 and x 0 is 10 10 10 10. So, if I add up I will get 10 1 0 0 1 0 1, they are same, and therefore, we have obtained a collision, and therefore, this is not a secure hash function. By this I end today's lecture, and this is the last lecture of our course. I hope that you have enjoyed the course, and I wish you all the best for the final examination. Thank you very much.